Let's begin. We're going to talk about doing unit conversions today. And we're going to start with some of the things that we discussed last time. One of the things we discussed last time were the metric prefixes. So let's first list the metric prefixes that we're going to be using. We have nano. Nano is the same thing as 10 to the minus 9, and it's abbreviated with the letter N. Then we have micro. Micro is 10 to the minus 6, and it's abbreviated with this Greek letter mu. Milli, that's 10 to the minus 3, abbreviated with an M. Centi, 10 to the minus 2, the letter C. And then we skip up to the positive exponents. Kilo is one that we want to talk about. That's 10 to the 3. Letter K. Mega, capitalized. 10 to the 6, 1 million. And then finally, giga, capitalized. 10 to the 9, 1 billion, capital G. Those are the metric prefixes that we want to use. And we're going to combine these with units. We want you to think about units as something very similar to numbers, in that most of the time when you see a unit, you'll consider it to be multiplied by the numeral and the prefix that comes before it. Now there's 7 basic metric units that scientists recognize, but we're only really interested in 4 for this class. So we'll mention what those 4 are and what they measure. We'll put them right here. The first thing that we're going to look at is a measurement of length. Length is measured by meters and is abbreviated M. We've already discussed that one. We're also going to look at measurements of time. Time is measured in seconds and abbreviated with S. Of course, it's measured in hours and days as well, but the base unit is seconds. Then we'll look at mass. Now, mass is an interesting concept. People often confuse mass and weight. Think of them as the same thing. Weight is a slightly different concept. Weight is the response that mass feels due to gravity. Mass is the amount of stuff that's in an object. But weight is what the response is because of gravity. So if you travel to a different planet, you'll have a different weight, but you'll still have the same mass. When people talk about losing weight, what they normally mean is they're trying to lose mass. Now the base unit scientifically for mass is the kilogram, but because we have kilo listed over here, we're going to shorten that up. We're going to ignore the fact that we have that prefix there and just think about the gram. That's sort of what we're going to start with. This is usually abbreviated as a G. And then finally, the last thing we're going to look at is temperature. Temperature is measured in Fahrenheit in the US. Everywhere else in the world they measure it in Celsius. And degrees Celsius is the same thing we're going to be using. But instead of keeping 0 at the freezing point of water, we're going to use the Kelvin scale. And Kelvin goes all the way down to the coldest temperature possible. That's 0 Kelvin, absolute 0, abbreviated capital K. So those are it. That's the 4 that we're going to use. Now you can take any one of these measurements and any one of these prefixes and come up with new units. So let's do that right now. We'll take these measurements, we'll just take a random prefix. Let's take K, kilo, and a random measurement here, second. This is the kilosecond. And because we already know how the prefixes work, we know what a kilosecond is. A kilosecond is the same thing as I can just replace kilo with 10 to the 3. And seconds is the base unit multiplied by. So here we have a very interesting statement. This statement we call a conversion factor. It tells me how to translate between one unit, the kilosecond, and another, the second. This was a very easy conversion factor to come up with because I know the rules for metric prefixes, and I know that the units are going to stay the same. But the idea is that if I measure a kilosecond of time, a kilosecond of time is about 20 minutes or so, I can automatically say how many seconds that is. Now this conversion factor is easy to say in English, but if I want to use a different form, it might be more helpful to have a different conversion factor that I'm going to manipulate mathematically. And that type of conversion factor, the one that's more useful, I usually call a fancy form of the number 1. And you can obtain that just by dividing both sides by one of the things that's on either side. So if I start off with a kilosecond, for example, I could divide both sides by a kilosecond. And when I divide kilosecond by kilosecond, I get 1. And when I have 10 to the 3 on this side, seconds, divided by a kilosecond, all I've done here is I've rewritten this conversion factor in a more convenient mathematical form. This says that 10 to the 3 seconds divided by a kilosecond is 1. Now, why do I want to do that? Well, it's going to be interesting for when I'm trying to do some mathematical conversions. But this isn't the only form, the only fancy form of 1 that I have. I also have another one. If I take the reciprocal is just switching the numerator and the denominator. Any fraction that's equal to 1, if I switch the numerator and the denominator, it stays 1. So I can flip this, and I come up with a different conversion factor. That is 1 is equal to 10 to the, sorry, now I flipped it. So 1 is equal to a kilosecond divided by 10 to the 3 seconds. These two mathematical statements are going to be more important and more used than this one up here, although they all mean the same thing. Now, why is this? If I ask a question that asks me to convert between one unit and the other, these are going to be the more important and the more useful conversion factors. So the example that I might give is, how many seconds in, and I can use whatever number I want, 75.2 kiloseconds. How do I answer this question? There's a number of ways to answer it, but if I'm going to use the techniques of conversion factors, what I would do is I start with what I know. The thing that I know is that I have 75.2 kiloseconds. Often it's the last thing that's mentioned in a question. That's what I know when I'm doing a conversion. So I'll start with 75.2 kiloseconds. And now I'm going to choose, I'm going to multiply by 1. That's not going to change the amount of kiloseconds that I have, but it will end up changing the units at the end. So if I start off with this kiloseconds, I have to choose which conversion factor I want. I can use either one, but one is more convenient than the other. And the one that's more convenient is the one that gets rid of the thing I don't want. I don't want to have any more kiloseconds. I want to get rid of it, and I want to switch it into seconds. So in that case, if I put kiloseconds in the denominator, it'll cancel the kiloseconds that's up here in a numerator, and I'll end up with a converted unit. But it's the same amount. It's the same measurement. It hasn't changed because I'm only multiplying by 1. So that's what I'm going to do right now. I start with 75.2 kiloseconds. Now I'm going to take this first conversion factor, 10 to the 3 seconds, divided by a kilosecond. That doesn't change the measurement because it's still the same measurement because I multiplied only by 1. And I can cancel kiloseconds and kiloseconds. And now it's simply a matter of doing a simple multiplication problem. So I have 75.2 times 10 to the 3. Kiloseconds have canceled and I'm left with seconds. This is an improper scientific notation. 75 is in the tens space. It's in the tens generation, so I know that that's the same thing as 7.52 times 10 to the 1. But I can't forget my times 10 to the 3. And I have seconds here, so those are equivalent. When I multiply 10 to the 1 times 10 to the 3, the exponents add. So here, I have my final answer, 7.52 times 10 to the 4 seconds. And for our purposes, you could round that to 7.5 or even 10 if you really wanted to. Let's just leave it at 7.5 times 10 to the 4 seconds as our conversion. Otherwise, we could call that 75,000 seconds. That's how we convert it. So this was a long way around. I could have also just substituted kilo for 10 to the 3 and done it that way. But I wanted to give an example for how this conversion factor works, because sometimes it's a little bit more complicated than that. And I'm going to give an example. But before I give an example of that, I want to talk a little bit about how to solve problems that might be posed about calculations, about sizes, dimensions, distances, times, masses, and so forth. Call these math problems or calculated problems. And there's a lot of different techniques that people use to solve these problems. But the technique I'm going to discuss is one I call the PACE method. One of the advantages of this method is that it allows you to start even if you don't know where to start. So sometimes that's one of the biggest questions that people ask. I don't know how to start a problem. The PACE method gives you a starting point automatically. You just remember what each of these letters stand for. The first is called picture. So the first thing you usually do when you're trying to solve a problem is draw a picture. And sometimes it doesn't make sense to you right away why you're drawing a picture, but often when you draw a picture and you start to label things that you know, it becomes a little bit easier to solve the problem. You begin to see some relationships that you might not otherwise see. So the question I'm going to try to answer is how many seconds are in a year? Last time I gave the answer to this. So I'm going to give the answer again, because you could look this up online if you wanted to. But the number of seconds in a year is about 3 times 10 to the 7 seconds. Right? So if I just knew that, I could answer it and be done. But let's imagine I didn't know this. And let's imagine I didn't have access to the internet or a resource where I could look this up. How would I answer this using the conversion factor techniques that I was looking at? Well, let's go through the PACE method. I'll go through each of the steps. We already know the first one, it's picture. So the first thing I'm going to do is draw a picture. So the picture I'm going to draw is, well, I want to know how many seconds, so I like to draw seconds as a clock, are in 1 year. I don't know, maybe draw something like a calendar. That's my calendar. I want to know how many seconds go into this year. That's my picture. Now in this case, the picture doesn't mean as much as it might in other situations. But it's still good to do this because it gives you some sense of what you're doing. And in fact, one of the big things that you need to do next is analyze the problem. That's the A. And to analyze the problem, you pick out the things that you know, and you try to figure out the things you don't know, and try to figure out what type of answer you want. In this case, we know we want an answer of seconds, and we're starting with 1 year. So when you start off the problem, it's good to know what you already have. We know we have 1 year. But then how are we going to convert this year into seconds? There's a number of different conversion factors that we have at the tips of our fingers that we've memorized over the course of our lives that we can use to answer this question. And the first one is, how many seconds are there, for example, in a minute? Now, we all know that there's 60 seconds in 1 minute. That's a conversion factor. Now that form isn't useful necessarily, but we can convert it into the useful forms, the fancy forms of 1. Then we have 60 minutes is 1 hour. 24 hours is 1 day. And 365 and a quarter days is 1 year. And at this point, we notice that we have a year here and we have a year here. So we could use this conversion factor down here to get rid of the year. Could convert it into days, in fact. The tendency might be to do that right now. Convert it right now and then have a number of days. But the thing that we actually want to do is continue to set the problem up. We're still just analyzing. The next step, after we finish analyzing, will be calculate. But we're actually not done yet. We still want to continue to set this problem up. In fact, in general, when you set one of these problems up, you want to set as much up as possible before you actually do any of the calculations. So we're going to try to avoid calculations until it's absolutely necessary. So I don't have to do any calculations yet because I can convert a year into something else by multiplying by a fancy form of 1. The question is, do I put years on the top or years on the bottom in the conversion factor? So hopefully you can see that I should put 1 year on the bottom and 365 and a quarter days on the top. That way the year will cancel. I still don't have the number of seconds I want though. I have the number of days. Now I want to get rid of days. I can use this conversion factor to do that. Put days on the bottom. And I put 24 hours on top. That's the fancy form of 1.5. Still don't have seconds, so let's continue on. If I get rid of hours, I can get rid of hours by saying 1 hour is the same thing as 60 minutes. And I can get rid of this final minutes by saying 60 seconds is 1 minute. Now if I go through, I'll see that the units, which are multiplied by the numerals, are going to cancel all the way down. And I'll be left, if I do this mathematics correctly, out with the number of seconds that are in a year. So let's see what that looks like. I've got 365.25 times 24 times 60 times 60, and then seconds are left over. That's all of the things that are left. I've got ones on the bottom, I can ignore them. That is the mathematics that I want to do. I still haven't started calculating, I'm still analyzing. But I'm going to continue to do this, and in fact, I can put this in my calculator, for example, get the answer really quickly. But I can do this without a calculator. Let me show you how. I'm going to first change all of these numbers into scientific notation. So I have 3.6525 times 10 to the 2 times 2.4 times 10 to the 1 times 6 times 10 to the 1 times 6 times 10 to the 1 seconds. So I still haven't done any calculations yet. I've just rewritten these in scientific notation. And if you can't recall how to do that, you should look back at the last lecture. Now, I'm almost ready to calculate, but I want to remember one fact about multiplication. I can multiply numbers in any order. And in particular, I'm going to collect all the 10 to the powers on one part, and I'm going to look at all the leading terms, the a, we say a times 10 to the b, on another side. So first we want to count up our powers of 10. We've got 1, 2, 3, 4, 5 powers of 10. So it looks like whatever answer I have is going to be times 10 to the 5 seconds, just by adding the exponents because I'm multiplying these numbers. And now I'm going to look at the leading terms. I've got 3.6 times 2.4 times 6 times 6. See, I'm doing the calculation now. Well, some of this is easy to do. I know what 6 times 6 is. 6 times 6 is 36. And now I have 36 times 2.4 times 3.6525. Well, 36 times 2.4, that's pretty close to 10. Times 10. 36 times 2.4 is about 100. 10 times 10. It was 3.6 times 2.4, it would be 10, but I have 36. So it's 36 times 2.4, about 100. Now I happen to know that that's pretty close to the answer. If you didn't know that, you could have done another one. This is all about estimation, as well as we can. We're going to estimate. So I have 100 here, and I'm going to multiply 100 times 3.6 or so. So I have 3.6 times 100. That's going to be about 300 or so. I could have called it 400. I'm going to call it 300. So I multiplied that 100 that I got from here times 3.6. I got approximately 300. This was a little bit of an above estimate. This is a little bit of a lower estimate, but they both seem to work pretty well. Okay, so now I have my leading terms that have given me a full extra factor of 300, but I can't forget what I had done with my tens. That was times 10 to the 5. And I still have seconds here. So I have 300 times 10 to the 5 seconds, which is the same thing as 3 times 10 to the 2 times 10 to the 5 seconds, or 3 times 10 to the 7 seconds. And that's what I say the number of seconds in a year are. Notice I started with a year, I went through my argument, and I ended up with the number of seconds are in a year. The final point in PACE is evaluate. Picture, analyze, calculate, evaluate. When you're finished, you shouldn't just put everything down and stop. You should think about whether or not the answer that you obtained makes any sense. And in this case, I can say pretty certainly that it does, because I actually knew what answer I was supposed to get ahead of time. I knew it was something like 3 times 10 to the 7, and here I got 3 times 10 to the 7 seconds on the bottom. But in other cases, you may not know what the answer is. You still should think about ways to evaluate. Are you expecting it to be a big number or a small number? If it's a big number, and you have something 10 to the minus a big number, that's probably not the right answer. So there's lots of different ways and techniques that you can come up with to decide whether or not you've answered the question in a reasonable way. Evaluate whether your answer makes sense. And that's an important step that people often forget, this evaluation. Let's try another problem to see if we can answer it. How many seconds in a year? Let's look at another question. I want to answer the question, what is the surface area of Earth? So let's do this one. The first thing I'm going to do is I'm going to draw a picture. So I draw a picture of Earth. Picture of Earth right there. And I'm trying to decide what the surface area of the Earth is. Now, I might be able to just look this up, or I might know some facts about the Earth. So one of the facts I know about the Earth is I know how far it is from the center to the surface of the Earth. You could look this up in the back of your textbook, for example. This is called the radius of the Earth. The radius of the Earth is often given this symbol, R, a circle with a cross in it. That's the radius of the Earth. And it is 6,300 kilometers. So that's one fact I have. I'm starting to analyze here. I want to know surface area. So I should try to think about surface areas. Now, I can assume that the Earth is roughly a sphere. And you may recall that you learned what the surface area of a sphere was at some point in time. You knew what this was, or you had seen it before. You may be able to look it up. It's 4 times the special number pi times that radius, the distance between the center and the surface squared. That's the surface area of a sphere. Now in our class we're into estimation. Because we're into estimation, we're going to be okay with saying that pi is approximately 3. That's not a bad approximation. So I'm going to rewrite this as 4 times 3 times the radius squared, which is the same thing as saying 12 times the radius squared. So that's on the analysis side. I'm still just analyzing right now. I haven't done any calculations. But I know what that radius is. I looked it up, or I actually knew what it was in this case, so now I can push it in here. And I've got 12 times 6,300 kilometers squared. Still haven't done any calculations yet. But now I've sort of run out of chances to analyze. I'm ready to do some calculations. So what am I going to do? Move over here. The thing to think about for this problem is I'm first going to want to square everything. And that means squaring 6,300, and also means squaring kilometers. It means squaring the units. Well, I still have 12. But now I have 6,300 squared. And I also have kilometers squared. I like to put the full unit in parentheses, and you may see why in a bit. Okay. Well, how do I square 6,300? Again, the technique is to change this into scientific notation. So this is the same thing as 12 times 6.3 squared times 10 to the 3 squared. When you square a number, you square all the things that are multiplied by. And so in this case, it was 6.3 times 10 to the 3. I just pushed that squared into both sides. You could have also looked at that a little bit more carefully. You could have written out 6.3 times 10 to the 3 squared and then separated it, but I skipped a small little step there. And I'm going to use the shorthand still now, which is just to say km squared. But you should be aware that that squared isn't just squaring the meter, it's also squaring that kilo prefix. That's an important thing to remember. So 6.3 squared, that's pretty close to 36 or 40, or maybe even sort of close to 50, not quite 50. Let's call it 40. There's still a 12 right here. 10 to the 3 squared is 10 to the 3 times 10 to the 3, which is 3 plus 3, which is 6. When you raise an exponent to another power, you multiply the two exponents together. So 10 to the 3 squared is the same thing as 10 to the 6. And I've got kilometers squared right here. All right. Well, this is 12 times 40, which is the same thing as 12 times 4 times 10. Right? 12 times 4 times 10. I know what 12 times 4 is. 12 times 4 is 48. And 48 is very much like 50, so let me call it 50. Which is the same thing as 5 times 10 times 10 times 10 to the 6 square kilometers. And if I multiply these two things together, I get 10 to 10 times 10 times 10 to the 6, that's 10 to the 8 square kilometers. And I have this leading 5 left over. 5 times 10 to the 8 square kilometers. Well, I know that that's fairly close to the actual number. It's within some 10 or 20%. That's pretty good. If I just declared this to be the area of the Earth and didn't evaluate, I should sort of warn myself that I might have done something wrong. So let me think about this. How could I evaluate this question to decide whether I got the right answer? I know I started off with about roughly a few thousand, almost 10,000 kilometers in radius. And I know when I look for an area based on a length, typically that's a square. So if I start off with something like 10 to the 3 or 10 to the 4, and I square it, I should be somewhere in the realm of 10 to the 6 to 10 to the 8. And that's exactly where I am. I'm right up about there. So I'm pretty happy with how these two things seem to work out. But I could even go further if I needed to. What if it asked me for what the area was in meters, for example, square meters? I could do that actually very simply. I could come up with a conversion factor if I wanted to. But I can also recall that K is the same thing as 10 to the 3. So I can push that in here, and I have 5 times 10 to the 8 Now k would be 10 to the 3, and I would just put in 10 to the 3, except I have to remember that whenever I square units, I square the prefix and the unit. So the prefix is 10 to the 3, and the unit is meter, and I squared both. So 10 to the 3 squared and meter squared is what I'm going to end up with. So I have 5 times 10 to the 8, and now I have to distribute that squared again, times 10 to the 3 squared, which is 10 to the 6, meters squared. 8 plus 6 is 14. So I have a total land, or a total area, surface area of the Earth, of 5 times 10 to the 14 square meters. That was a unit conversion that I did without doing the conversion factors, which I could do because I know how my metric prefixes work. That's a sort of a shortcut. Now I should think carefully about this because I started with 10 to the 8 square kilometers, I ended up with 10 to the 14 square meters, and I should evaluate, does that make sense? And indeed it does, because I know that there's 1,000 meters in a kilometer, so there should be 1,000 times 1,000, 1,000,000 times more square meters than there are square kilometers, and that's exactly what I have. I have 10 to the 6 larger. So that's another answer. If it had asked me for square meters, that's the answer. So that's a quick discussion of how to use conversion factors, how to use some of the problem-solving techniques to answer certain problems. I hope that was helpful, and we'll have one more exploration of one more set of mathematical techniques to do, but that's what we'll end this with. Thanks.